All right, all right, all right. Let's get on it. Let's do our end behavior for rational functions. F of x is going to be some p of x over q of x. We're going to treat it as a polynomial for now. It's definitely what we want to do. We've got ax. The book does n on top, and I didn't realize that until I was all the way through all the lecture notes. Book does n here and m on bottom, and I didn't. And it will change some of it, but not everything. So just follow what I'm doing. Note that the book will say something slightly different based on m and n. What we're going to do is we're going to divide p and x and q of x by the highest power in the denominator, which is our x to the n, okay? This will show us which term dominates the behavior for large x. That is the term we're using. We're not looking at the b. Just do the x to the n. And you'll see that it's a little bit easier on your paper space, based on your paper, if you multiply by 1 over x to the n instead of dividing by x to the n. We're going to look at a couple setups. Let's start off with f of x equals 3x minus 1 over 2x minus 5. We can see here m on top is 1, n on bottom here is 1. And the largest term on bottom is 2x, but we're going to use x, not 2x. We're going to multiply by 1 over x, and now we're going to start writing in the limits because we're looking at the limits now. And make sure, again, remember, keep writing limits down until you actually take the limit. Okay? So when we get here, as we saw before, when we take something going to infinity and x is in the bottom, the bottom goes to infinity, so the overall thing goes to 0. And so that goes to 0 as x goes to infinity. We're actually left with 3 halves. So we will have a horizontal asymptote of y equals 3 halves here. Will x to the negative infinity be any different? You'll notice, like, we're looking at it over here, plugging in negative infinity. I'm sorry, you can't see what I'm pointing at. We're looking at it over here. If we plug in negative infinity, it's not changing anything. That's still going to 0. So it'll be the same for x going to negative infinity. All right, let's take a look at the next setup. We've got 5x squared minus 7x on top, 3x cubed plus 2x squared minus x plus 1 on bottom. So my m is 2, my n is 3. And what should I multiply by? Take a look at it and see what you come up with. If you said, let's use the highlighter, x cubed, you were right. So we're going to multiply the top and bottom by 1 over x cubed. Remember, you got to distribute it to both. Distribute, distribute, distribute. And here, distribute to all of them. We end up getting the limit as x goes to infinity of 5 over x minus 7 over x squared on top. The bottom is 3 plus 2 over x minus 1 over x squared plus 1 over x cubed. Anywhere where there's an x on bottom, that term goes to 0 with x going to infinity. So these are all going to 0. We get 0 over 3, which equals 0. So our horizontal asymptote is y equals 0. And by the same reasoning above, x going to negative infinity isn't going to be any different. Okay? Next example, we've got f of x equals 4x squared plus 9x minus 2. And the bottom is 2x plus 1. You'll notice m here is 2. N here is 1. And what should we multiply top and bottom by? Hopefully you said 1 over that, 1 over x. So we're going to multiply by 1 over x. Shoot, I was trying to get rid of the highlighter for when I record the video or post the lecture notes. We're multiplying by 1 over x. So the limit as x goes to infinity now becomes 4x plus 9 minus 2x on top. On bottom, we have 1 minus, or 2 plus 1 over x. As x goes to infinity, that goes to 0, that goes to 0. This goes to 2x plus 9 over 2. Okay? So, as x goes to infinity, shit. So, let's do that as a subset. That kind of looks like 2x plus 9 over 2, but x is going to infinity still. So, this will be infinity. The limit will be infinity. Let's take a look at the graph of this one, because this one's a special case. If x is negative infinity, what happens? The limit should be negative infinity, because we've got it down to 2x plus 9 halves. That's going to negative infinity. This should be negative infinity now. So it will change. In this scenario, we had p of x over q of x, and the degree of the numerator to the top was 1 larger than the bottom. This actually generates a special scenario, and hopefully we can see it by looking at the graph. If we look at the graph on the left, look at this. As x goes to infinity, that's going like that, and that's going like that. And kind of like if I connected the dots, this looks like a line, doesn't it? Well, it turns out it is. Let's do some polynomial long division. With the bottom having a coefficient of 2 rather than 1, synthetic division is not that friendly here. So we're going to do long division. And when I did the long division, I got 2x plus 7 halves. And then I had a remainder of minus 11 over 2. And so the remainder goes over the old denominator. So we had the denominator 2x plus 1. The 11 over 2 goes over that. And even though I didn't show it, negative 11. Oops, let's get off that pin. Negative 11 over 2 over 2x plus 1. When we clean up fractions, does look like that. So I distributed, when I went from there to there here, I distributed the 2. This is kind of like what it's looking like here. And it's exactly what it's doing if we do the division. So if we ignore the remainder part, let's just graph the 2x plus 7 halves. I did this on Desmos and it generated this blue line. And look at that. Look at that beautiful, glorious image. There's my line that I got from polynomial long division. And it actually is the line that our function, our orange function, is following along as it goes to infinity. I didn't do that very well with highlighters, but I think you get the gist. It's showing asymptotic behavior. When we have a asymptote that goes at a diagonal like that, we call it an oblique asymptote. Another name for this is the slant asymptote, but that's just because people are lazy. It's called the oblique asymptote. But if you hear slant asymptote, they mean the oblique. So we've got a bunch of special case scenarios. Let's look at what we did. We talked about rational functions and doing limits here. Again, I was using m here. Oh, wow, that it. Want my highlighter here. I was doing m there and n here. Pay attention to that for the following here. So if m equals n, so the degree on top and the bottom is the same, You will find after you do the multiply by 1 over x to the n, this is, you still need to do these steps. You still need to multiply by 1 over x to the n. You're going to see that the limit leads to the coefficients. That's all that's going to be left. Okay? You still have to show the work, so the limit will be a over b. You'll have a horizontal asymptote of y equals a over b. Now, the next scenario we did was when the bottom was bigger, so m is... I got this sign mixed up here. Let's fix that. If m is less than n, the top is smaller than the bottom. We did this case. We ended up, everything on top had a 1 over x or higher, and we led to a limit of 0. And so a horizontal asymptote will be y equals 0. That's when the top has a degree that is smaller than the degree on bottom. The third scenario is when I need to change the sign here. If m is greater than n, or top is greater than bottom for degrees, we can rewrite if we did polynomial long division. This was done with polynomial long division. Or if you can get away with it, synthetic division. But we got another function h of x, and then some remainder. In our last case, it was negative 11 over 2 over our original denominator. And so when we look at the limit here, r of x always has a degree smaller than q of x. This is always 0. Bye. That is always going to 0 because the top is smaller degree than the bottom. So we're left with like limit as x goes to plus or minus infinity h of x. This is going to lead to infinity or negative infinity. That didn't change with the oblique asymptotes. Let's go look at that real quick. The oblique asymptotes are still going to infinity and negative infinity. We just know how they're going to negative infinity or positive infinity. And so we're going to make a little subcategory here of m greater than n when m equals n plus 1. So the degree is on top is just 1 larger than bottom. H of x will also be an oblique asymptote in addition to the infinity or negative infinity. And that all depends on n behavior and stuff like that, and the coefficient and all that. You really want to do the limit and see how stuff plays out. Don't just take these as shortcuts. And that's what I got for now. I'm going to do more videos. I'm going to do right up the lecture notes tonight, do more tomorrow. Because we've got 2 days of this topic. Peace. Take care, y'all.